screen too. I have the algorithm. I have my Visual Studio Code open. I have the algorithm. Let's see. We are good to go. All right. So I'm sharing my screen right here. I'm going to go down like a nice little rundown of this algorithm here. I'm going to kind of like walk through it step by step, but you were here for last week, or Tuesday actually, where we went over the brute force solution, which is just really as inefficient as it gets, just checking every single palindrome. The expand around center, where we're kind of going over each character in the substring and just expanding from that, figuring out which one it is. And then the dynamic programming, which was much different than the first two solutions, but not really efficient. Not really efficient. Like, you don't want to use this one, honestly. The Manacher's algorithm is, I look at like an optimization around the expand around center. And so basically the first thing we do, when this is going to be the string we're using for this example, the first thing we do is we just check if it's of length 1. If it's of length 1, we're just going to return right away. So then the next thing we do is, with Manacher's algorithm, if it's an even number palindrome, like let's just say there's a BB in the middle here, and it starts with an even number, Manacher's algorithm isn't going to be able to find even number palindromes. And so what we do is we pre-process the string. We pass this into a function called pre-process, and we add a caret on the left, we add a $sign on the right, and then we add a hash letter for everything else. So it looks just like this right here. So we have the caret on the front, $sign on the end, and then it's just hash character, hash character, hash character. And this way, let's just say we have two B's in the middle, and that's where the longest palindrome starts. We're not going to have to account for even palindromes, because there's going to be this character in the middle. So it's automatically going to account for the two B's. It's going to turn the two B's into an odd length palindrome. So the only thing we're analyzing with this string is odd length palindromes. And at the end of the algorithm, we'll do what we have to do to remove these from our final analysis to return the correct string. So after we pass this into this pre-process function, which this pre-process function is super simple. You pass the string in. Like I said, the first thing you do is this. Then you iterate over this string, and for each character, you just add hashtag character, and then at the end you do that and output it. So that's how we get that. Next, we're going to find the length of the modified string. So the length of this modified string is n equals 23 here. And then the last thing we're going to do before we actually start iterating over this and trying to determine the longest palindrome is we're going to create an array to store some information. And so basically what we're doing is we iterate over this modified string, is we're going to be storing the value of the longest palindrome at every current position. So you could see like this A right here, it's a palindrome of length 1 or length 3, but from the center position we're 1 out. So one out this way, 1 out this way, so there would be a 1 right here. For this B right here though, you could see it has hash AA hash, so we'd store 3 right here. And so we're basically storing with this position what is the longest palindrome up to this point. With this character as the center, we're keeping track of, with this character as the center, how big is that palindrome basically. And then we're going to create a pointer to track the center of the working palindrome, because as we move to the right, we're going to keep track of the rightmost palindrome at any given point. I'll show you the value of that in just a minute. And we're going to create a pointer to keep track of the right boundary. So we're going to have a center pointer to keep track of where the center of the rightmost palindrome is, and we're going to have a right boundary pointer to keep track of where it ends, basically. And then we're going to start iterating over the modified string starting at position 1. We know we don't have to iterate over this right here because that just doesn't matter. That's irrelevant entirely. So let me just move this down so we could do this walkthrough a little bit. And so there's going to be, like I said, there's going to be 4 variables we're keeping track of. So let me just move this up here. So like I said, we're keeping track of our center, the center of our current working palindrome. We're keeping track of the right boundary of our current working palindrome. We're keeping track of the current palindrome, the center of the current palindrome that we're analyzing. And we're keeping track of the mirror of the eye position. So let me go ahead and, so let's say we initialize this for loop. We're going to start iterating over our palindrome starting at position 1. Center is starting as 0. So we'll start right there. Mirror doesn't have a value yet. Right is also initialized as 0 for now. So the first thing we're doing is we are going to find our mirror, basically. So we want to find, if this is our center, we want to find the mirror of eye. And so what we do is we do center times 2 minus eye. So center times 2 in this position is 0, minus 1 is -1. So mirror is actually outside the bounds of the array. And so the next thing we do is, so we are finding the mirror. We check to see if I is less than the right boundary. And in this case, I is not less than the right boundary. I is on the right side. But for most of the algorithm, I is actually going to be on the left side. It's going to be less than the right boundary. And then we expand from center. We expand from the center by doing basically what we want to check is PI plus I plus 1. So PI is 0 plus I, which is 1, plus 1 is 2. So 0, 1, 2. So we're starting right here. This is A. And we do PI, which is 0, minus I, which is 1. So we're going to end up in this position. So basically we're comparing this character and we're comparing this character, and while they're true, then we would increment PI. But since they're not true, since this character does not match this character, then we break out of that while loop. And then if I plus PI is greater than the right boundary, we create a new working palindrome by setting the center as I and the right boundary is I plus PI. And so since I is greater than the right boundary in this case, then we'll say, center equals I, right boundary equals, let's see, and right boundary is I plus PI. So since PI is 0 and I is 1, our right boundary, oops, is actually right here on 1 as well. So this is our current working palindrome right here. So basically, now what we do, that's the end of our loop. And so we increment our I to here. The first thing we're doing again is we're finding out what our center is. Our center is on the 1 position. We need to find out what our mirror is. So we take the center's value, so 1 times 2 minus I. So 1 times 2 is 2 minus I, which is 2. So our mirror is 0. And we move that right there. And so you can see our current working palindrome is very small. It's just 1 character right now. And so again, we just check to see if I is less than our right boundary. And if it is less than our right boundary, we're checking that to see what value we can store right here. But since I is greater than our right boundary, we actually don't even execute that right there. The first thing we want to do now is we want to run, let me actually create another one right here, because if we have equals 2, our mirror equals 0, our right boundary is 1, our center equals 1, and then so basically this is our P array. So what I want to do is I want to calculate I plus PI, which is 0 plus 1. So I is 2 plus PI, which is 0 plus 1 is going to give me 3, because 2 plus 1. So it's going to point to this right here. And then I'm comparing that character with I minus P1 minus 1. So since this is 0, I is 2, and we're subtracting 1, we're comparing this character with this character here. And since these characters match, we're going to change this to 1, because they match. And then we're going to do it again. So we're going to do I plus PI, which now PI is 1. So we have I, which is 2, plus PI, which is 3, plus 1. So now we're at 4. Now we're pointing to this B. And also I minus PI, which is 1, minus 1. So now it's pointing here. And these don't match. And so we just break out of that while loop right there. The reason why we run that while loop is basically that's our expand from center. That's our expand around center, that while loop right there. We're incrementing this P position right here until we reach 2 characters that don't match. And so what we're going to do is we're going to use this information later on, because we're keeping track of basically the palindromes that we encounter, and we're able to use this information later on in the like over the iteration. We're going to be able to use this information here. And so what we do next is we check if I is less than right boundary, find out which is smaller, RB, expand, we did that. So if I plus PI is greater than RB, which it is, because we have our I equals 2, our PI equals 1, so that equals 3. It's greater than RB, our current right boundary of our current working palindrome is only 1. So in this case, we create a new working palindrome. The center of our new working palindrome is here. And then we set our right boundary is I plus PI. So our I equals 2 and our PI equals 3. So 0, 1, 2, 3. So now we actually have a new right boundary. Our new right boundary is here. So you can see this is our new current working palindrome. It's basically this. This is our new current working palindrome. And so same thing. Now what we do is we increment I, First thing we do is we find out where the mirror of I is by multiplying our center by 2. So now our center is at 2. We multiply that by 2, which gives us 4, minus I, which is 3. So 4, 3, 2, 1. Our mirror is right here. And so the first thing we do is, here, let me just make this easier to find out where the, there we go. Oops. All right, so we find our mirror. If I is less than right boundary, in this case, I believe I is on our right boundary, right? So it's not. It's not less than. It's actually on our right boundary. So in this case, we know that whether this mirror's position is less or right boundary minus I is less, it's going to be 0 no matter what. So you'll see why that makes sense in a minute too. So basically what we're doing now is we're expanding around center from this position here. We're using I plus PI, which is 0 plus 1. So we're comparing this B to I minus PI minus 1 and this A, which they're not matching. So we don't do anything. We don't increment PI. And so what we're doing now, let me fix these values here. This is now 2. This is 3. This is 3. This is 1. And so what we do, because we expanded around center, if I plus PI is greater than right boundary, so I is at 0, 1, I is at 3, right boundary is at 3, PI is 0, so I plus PI is 3, right boundary is 3, and so I plus PI is not greater than RB, so we don't update our current working. We just increment I. So we go ahead and increment I. This is where we get a larger current working directory. So the first thing we do is we find our mirror. Let me update this. Now I is at position 4. So we do center times 2, which gives us 4, minus I, which is 4. So our mirror is going to end up on 0. And we're using this mirror to collect information from the palindrome that matches this palindrome. So our I palindrome, later on, we're going to get the palindromes that are being pointed to that are centered at I. And we're going to be able to use this M to collect information from P to pass that information forward to I and start at mirrors P value so that we could kind of like skip over a few characters. Instead of, if we're at like a size 7 palindrome and the M palindrome matches our I palindrome, then and the M palindrome is like 5, then instead of analyzing those 5 characters, we're able to just start at character 5 and expand out to 6, then 7. So we're analyzing less characters. This M gives us the power to just pass information forward to this one right here. You'll see that more clearly as well. So basically, our current working palindrome is still here in the C. It's still this one here. And so we have our M. And then we're going to start expanding outwards. So the first thing we do, we're doing a while loop while PI plus I plus 1. So 4 plus 0 plus 1 is 5. So this hash is equal to PI plus I, or minus I minus 1, which is going to give us this hash. Then we increment PI. So now it's 1. And then we have PI plus I, which is 5 plus 1. Now we're pointing to this A, is equal to PI plus I, minus I minus 1, which is pointing to this A now. And they're matching. So we increment this to 2. And then we do it again. PI, which is 2, plus I, which is 4. So 6 plus 1, which is pointing to this hash. And then PI minus I minus 1, which is pointing to this hash. And we could do 3. So we increment that. And then we do PI plus I. So 7 plus 1, which is pointing to this X. And then we do, well, that's equal to PI. So 3 plus I, 4, or minus I. So 1 minus 1 is going to be pointing to this right here. So they're not equal. So we have the length of our palindrome right here. It's this. So you could see from our current center, we're 3 out. And so what we do now is if I plus PI is greater than RB, which it is, I is 4, PI is 3, so that's 7, then we set our new center as I. Our new center is I. And we set our new right boundary as I plus PI. So 3 plus 7. So 0, 1, 2, 3, 4, 5, 6, 7. So that's our right boundary because that's where the palindrome ends. So we could just keep that there for now. And now this is our current working palindrome. Centered at B, right boundary is R. So we increment I. Do you have any questions so far?
Not yet. I just wanted to ask if why do we need this mirror?
We need this mirror because this mirror is going to allow us to pass information forward.
I mean, you need this mirror to update PI?
Yes. Yes, exactly.
Okay. Yeah.
Exactly. You'll see that with this one. You'll see that in just a second.
Okay.
Which this one's an interesting case, but when we get here, it's gonna start making like a lot more sense. So the first thing we do when we start over this loop, I just incremented I to 5. Now we're pointing at this B right here. Actually 0, 1, 2, 3, 4, 5. Incremented I. So now we're pointing here. And so to find out our mirror, we do center, which is 4 times 2, which is 8 minus I. So 8 minus 5 is 3. So we're doing 0, 1, 2, 3. So you could see that our mirror now is pointing to this character, and the length of this palindrome was 0. So the length of this one, same thing, 0. That's the information we're passing forward right there. Since this is 0, so basically when I is on the left side of the right boundary, we're looking for which one is less. Either the position at M or right boundary minus I. So let's just say M was 5 and our right boundary was 7 and our I is 5, then we wouldn't replace this I position with 5. We'd actually replace this I position with 2. 7 minus 5. Because even though we had, let's just assume we had a 5 right here, there's no way that if the distance from I to R is 2 away from each other, that we could predict that this is 5. We know that it's 2, but we never gathered any information to the right of the right boundary yet. So we just don't have that information yet. So when I is less than right boundary, we compare two values. We compare right boundary minus 1, which would give us 2 in this situation. And with the value that's here. And if this is 0, then we use the 0. But if it was 5, we would just use the 2. And that'll become a little bit more clear when we get a little further down too. But 0, 1, 2, 3. So we're at the 3 position here. So if I is less than the right boundary, find out which is smaller. I is less than the right boundary. So we're going to do right boundary minus I, which is 7. Which is 7 minus 5, so 2. And compare that with the value stored at P mirror, which is 0. 0 is less than 2. And so we just keep this as 0 right here. Because that's less than this. And we're just using this palindrome to store its information here. And the reason why we know this palindrome has the same information basically as this palindrome is because this palindrome and this palindrome are both within the boundaries of our current working palindrome. If ever I goes outside our current working palindrome, we know that the mirror went outside our current working palindrome and that the information inside our current working palindrome is now useless. So we have to update our current working palindrome to move it to the right so that the information in our current working palindrome is useful. We want I and we want M to be inside of our current working palindrome. As long as I and M are inside our current working palindrome, the information stored in M is useful and we're able to pass it forward. But once I and M move outside of the right bound and the left bound, then the information inside of our current working palindrome is now useless because we never went outside the right boundary. So any information on the left boundary just is useless anymore. I has to be inside the right boundary for the value stored at M to be useful. So that's that. We would expand around center now. So PI plus I plus 1. So A, does that equal PI minus I minus 1B? No, it doesn't. And so we just check if I plus PI is greater than right boundary. So if 5 plus 0 is greater than 7, then we update our current working palindrome, but it's not. So we just go ahead and we increment I to the next one. We'll go ahead, increment I to 6. C is still that. Right boundary still 7. Mirror is actually going to be 2 now because we're using center times 2 minus 6. So if center stays the same, I moves to the right, we're actually going to move M to the left. And so in this case, this is the first time where we're going to be able to pass information forward, right? So the way that we processed this palindrome previously, we're not going to have to process this one. So the first thing we do is if I is less than right boundary, which I is less than right boundary, then we find out which is smaller. Right boundary minus I. So right boundary minus I is 1. P mirror is 1. And so what we're able to do here is we're able to store P mirror right there. So we take that. And now when we start our expand from center, we don't start with our first characters. We already have this 1. So we're doing P1 plus I, which is 7 plus 1, 0, 1, 2, 3, 4, 5, 6, 7, 8. So we're starting, you notice how we were able to skip this character here and just go straight to the next one? That's where the optimization comes in handy.
So you are bringing that data that data from the mirror.
Yep.
To update the current position on the PI.
Exactly. So we don't have to, if we weren't able to pass this information forward, then we'd have to compare this and compare this. But since we were able to pass this information forward, we didn't have to compare this and compare this. We were able to jump straight to this and this because P1 was automatically set to 1. So we're able to avoid comparing characters if we know that the palindrome matches. And we know that since what's up?
This is just when I is less than right boundary.
Right boundary, exactly. And I typically is less than right boundary, because if any point I passes right boundary, if I ever passes to the right of right boundary, we update our current working palindrome.
Yeah.
Yeah. So m equals 2. We did this. We saw that x does not equal b. And so what we're doing now is we're incrementing I to this one right here. This next character becomes a little more interesting to it and a little bit more clear as well. So as we increment I, we also decrement our mirror. So let's go ahead and set this is 1. This is 7. So same thing. First thing we're doing after we find our mirror, that's the first thing we do when we start a new iteration. If I is less than right boundary, I is not less than right boundary, I is right on the boundary. And since we don't have any information on the right side of the right boundary, there's no way we could, because we just haven't processed that yet. We haven't processed the right side. So even if m is like 5, it doesn't matter, because we can't assume that the characters on this side are matching the characters on this side. That's why we're always looking for the minimum. So now we're going to expand from center. Same thing. Pi plus I plus 1, which is going to target x. Pi minus I minus 1, which is going to target a. They're not equal, so we just do if I plus Pi is greater than RB. So I is 7. RB is 7. Pi is 0. And so it's not greater, so we just keep it. We keep our current working palindrome in the same position, and we increment I to the x position. So this is now in the 8 position. And so first thing we do is we find our mirror. This is pointing here. This is 0. So we're actually going to expand from center here. So 0 Pi plus I plus 1 is this hash. Pi minus I minus 1 is this hash. Or I should really be saying I minus Pi minus 1. It starts with I because I is the positive number. So we compare this hash matches. So we do 1. Now we do I plus Pi plus 1, which is this A. I minus Pi minus 1, which is this A. So 2. Then we do I plus Pi plus 1, which is this hash. I minus Pi minus 1, which is this hash. So we do 3. Then we do I plus Pi plus 1, which is this B. I minus Pi minus 1, which is this B. So 4. I plus Pi plus 1 equals this hash. I minus Pi minus 1 equals this hash. So 5. So we're 1, 2, 3, 4, 5 out. 1, 2, 3, 4, 5 out. So same thing. I plus Pi plus 1 equals this A. I minus Pi minus 1 equals this A. So 6. I plus Pi plus 1, this hash. I minus Pi minus 1 equals this hash. So 7. And then I plus Pi plus 1 equals this x. I minus Pi minus 1 equals this right here. And so this is where we break out. We have 7 right here. Now, if I plus Pi is greater than right boundary, and it is, I equals 8 and Pi equals 7, So 15 is greater than 7, which is our right boundary. So we set our right boundary as I plus pi. So we do, we move this to 15. So if this is 8, 9, 10, 11, 12, 13, 14, 15, right here on this hash, right before the x. So that's our new right boundary. Oops. Our new center is on I. So our new current working palindrome is this right here. Now we have tons of information. Now, the further I is within the right boundary, the more information we're going to be able to use. Because the larger our current working palindrome is, the better. Because then we're going to be able to account for even more. So just based on what we see here, is this is going to be 0, this is going to be 1, this is going to be 0, this is going to be 3. And so you could see where the optimizations are starting to come in, right?
Yeah.
And this is also going to be 1.
Like you are
mirroring. Yeah.
Mirroring. Yeah. That.
Mm-hmm. This is actually our largest palindrome. The B is the center, so we'll do that, and then we'll kind of break down and we'll look at the code. So let's just do a couple more examples. And all right, so I equals 9. Mirror equals, first thing we do when we start the new iteration is we take our center, which is now 8, our right boundary, which is now 15. So center times 2, 16 minus I. So 16 minus 9 is 7. So we move our mirror here. And so you see it's going to be 0 and 0. These are unmatching, so I'll go ahead and just increment I. We'll just skip this one pretty quickly. We'll move mirror. So as we increment I, we're also automatically bringing M down because it's just C times 2 minus I, so it's always finding the mirror. So in this case, this is where it kind of gets cool, because if I is less than right boundary, which it is, then we subtract I from right boundary. So we subtract 10 from 15, that's 5. So we're 5 away from right boundary on this side. And then we find out what this is. And we take the one that's less. So since 1 is less than 5, we take that 1, we store that there, and instead of comparing this with this, we're able to just jump straight to this and this, because P1 is 1 higher, so we just start 1 further out. And then same thing, we move here, we move here, we move here, we move here. So now we're at 12 and 4. And first thing we do is we subtract I from right boundary. So we subtract 12 from 15, which gives us 3. And then we also compare it with P mirror, which is 3. So we take 3, store it there. And you can see now that we avoid processing this whole palindrome. This we don't even have to process. We just start at the X, because P1 equals 3. So we do Pi plus I plus 1, which is going to give us this X, compared against I minus Pi minus 1, which is this X. So we increment this to 4, then hash, hash, then A, then hash, hash, then B, then hash, hash, then A, B. So this is where it breaks right here. We have 9. Now we check and we say if I plus PI is greater than right boundary, which it is. We have 12 plus 9, which is going to give us 21. Then we just set right boundary to 21. So 15, 16, 17, 18, 19, 20, 21. Right on this hash where the B and the A are unmatching. We set C here. Now our current working palindrome is massive, right?
Yeah.
Like this is good.
But I get the idea now, because it's like you are bringing information with this mirror index from on the left. That's the important thing. You are avoiding compare again with the values.
Exactly. With the expand around center, is O of n squared, but with this algorithm, it ends up being O of n, because you avoid so much.
Yeah.
Because if there are no palindromes, it's just O of n. If there are palindromes, then the more palindromes they are, which would typically force you to do more calculations, the larger they are, it actually, if you have big ones or you have more, then it actually decreases the computation you're doing as you accumulate more palindromes, which is like, as it would become less efficient, you have a strategy to keep it more efficient, which is super interesting.
Yeah, curious about computation of those with these pointers that matter.
Yeah, exactly. And so I'll move through it kind of fast now, and then we'll go ahead and we'll actually type out the code so you can see what it looks like. It's actually pretty simple, but there's definitely a couple things about the code where I had to really take a lot of notes and expand on everything that was happening. But yeah, so now we have 13 and 11. Both of these, it's 0. So 0 would be right here. A and B. So we go ahead and just move it here. Move it here. We're able to take this 1, because right boundary minus I is much greater than just this 1 that's stored here. So we can do that. First thing we do is compare the X and the B. We break out of that loop automatically. Move this, same thing, X and A. Increment this, decrement this. So we do right boundary minus I, so what do we, 12, 13, 14, 15, 16. So 16 and 12, 11, 10, 9, 8. So now we have a 7 here, and we have a right boundary and an I right here. So if we subtract I from right boundary, so 21 minus 16, we get 5. And in this case, we have 7. So normally we would put this 7 right here. But the thing is, our current working palindrome ends 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. It ends right here. It ends right here. This is where our current working palindrome ends. But this one, this palindrome actually extends 2 out. Well, we don't know what 2 out is over here. We haven't seen that yet. And so we can't put this 7 here. We have to put only the distance from I to R. That's the only thing we know for sure. We know that this palindrome is going to be at least 5.
Yeah, the minimum.
Exactly. Because we have this information, we don't have this information, so we have to take the minimum. This is something that took me a couple seconds to wrap my head around, but yeah. So instead of putting 7, we just put 5 there, and so we could start from 1, 2, 3, 4, 5. Now we could go ahead and compare this B with 1, 2, 3, 4, 5. This A, and so we just keep it at 5. So if we had put a 7 here, this would be incorrect, because this palindrome is actually only 5 out. This is it. So it allows you to maintain the accuracy of your your storage of your sizes. And so, yeah, you have that. I mean, this A right here is going to be 1. This B is going to be 1 because this one is 3, but we actually only have right boundary minus I in this position. We would replace it with 1. And then that would basically be it. We'd also have 1 right here. And this would end up being our total storage. So as you can see, we're just using the current working palindrome to figure out whether we're storing the distance from I to R or the position of P mirror. And if the distance from I to R is less, we store that here. If the position of P mirror is less, we store that here. And then we're able to just start calculating and processing our palindrome with a minimal number of calculations. And yeah, so this was really cool, man. It was like a constant, you're basically like collecting information from the string as you move along. So I thought it was really cool. Then based on this right here, we have this here. So we just, we set a max palindrome length to 0. We set a max palindrome center to 0. We iterate over the P array, starting at position I, where I equals 1, because we know this is in a palindrome. We actually know this is in a palindrome too. So we could start at 2 technically, I guess. And then if PI is greater than the max palindrome length, so if this is greater than the max palindrome length, which is started at 0, then we replace the max palindrome length with PI. And then we set our max palindrome center to I. So we would set our center to 2 in this case. We'd keep going. This is larger than our previous max length. Huh?
Are you going through this operation to find the center and the maximum length of the palindrome?
Mm-hmm.
Oh yeah. We could do that also in the while we are calculating the computing the palindrome.
Yeah, you're saying at any given time when you
yeah,
after we do the while loop expanding out, you're saying? Yeah, we could do that. I'm sure. Yeah. I don't see why not. I just separated it just for simplicity.
Oh yeah. To make it more simple. Yeah.
Yeah.
Oh yeah. I get it.
Separation of concerns kind of thing. Yeah, so you just iterate over this, looking for we're eventually going to find this is our max longest palindrome with a center of I, which is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So our center is at 12. And then what we do, you can see we find our start by doing our max palindrome center minus our max palindrome length. So 12 minus 9, which is 3, divided by 2. And so, and I believe we math floor it. I believe we'll math floor it. And then, so that would give us starting position 1, I believe. And if you look at, that would actually give us starting position 0, I believe. Because this is our greatest one here. No, it'd be starting position 1. Yeah. Yeah, math.floor. So max palindrome center minus max palindrome length divided by 2. That way we could actually run s.substring on our original string. The divided by 2 allows us to run it on our original string instead of on this one. And then we just return our original string with substring property, passing in the start, and the start plus max palindrome length. So let me go ahead and open up this right here. I'll type the pseudocode, I guess, and then if you want, you could type out the code. Does that make sense?
Yeah.
So we're just gonna check to see if the length of the string is less than or equal to 1. If it is, just return the string. That's the first thing we're doing. If it's 1, that's our palindrome right there. So we are going to run the preprocess function on our string to return a modified string. We're going to find the length of our modified string and store it in n, or whatever you want to call it, really. And then we're going to create our p array and fill it with zeros. Create our p array with length n and fill it with zeros. Then we're going to create our center variable and initialize it as 0. We're going to create our right boundary variable and initialize it as 0. And then we're going to begin iterate over our modified string. First thing we're doing on each iteration is figure out what our mirror is. I think you remember how to do that. I won't put any details, give you a little test there. And then we'll do if I is, I think greater, if I is less than the right boundary, then we're gonna store the minimum of, oops, my bad, running C commands over here. Right boundary minus 1, or p mirror then while the characters are equal to each other. This is like a little challenging, but I said it enough times where you probably got it.
Yeah.
Increment pi, and then we do if the sum of I and pi is greater than our right boundary, then we set a new current working palindrome. I won't go ahead and type that out either. Give you a little test on that one. And then, so that's basically our loop right there. And then after the loop, we'll create our max palindrome length. Actually, let me try to use proper language. Initialize our max palindrome center. And then we iterate over our p array. If our pi is greater than max palindrome length, and then we do a couple things. We set our new max palindrome length, set our new max palindrome center, And then after that one, we initialize our start variable by subtracting max palindrome length from max palindrome center and dividing by 2. And then we return substring of our original string starting from start and ending at start plus max palindrome length. That's it. That's the algorithm right there. Before you go ahead and type code though, does everything make sense? Do you have any questions? We'll go ahead and create this pre-process too. Think of any questions if you have any.
Not yet. I'm
Cool.
just going to ask for the link for
Oh, live share?
the live share link. Yeah.
Yeah, let me go ahead and post that here.
Thanks.
Yep. So pre-process, create an n variable with the length of the string. If the length of n is equal to 0, we can just return. What I did was I just returned this, so like the beginning and the end, and then
It
create.
looks like a regular expression.
Yeah, I know, right?
Yeah.
Initialize modified string as this. Iterate over original string, adding si with each iteration, and then add $sign to the end of the modified string after the loop, and then just return our modified string. Yeah, that's it. So that's it right there. That's the whole thing. I might have made a mistake or two, but I'm sure you'll find it if I did.
Okay. I think I'm going to start with. System modified string.
Mm-hmm. Yeah, you'll actually have to maintain a copy of your original string. So if you just replace the original string, then returning will be a little more, still possible, but just less simple, I guess.
Yeah. I'm going to skip this one because we are already checking the on this part.
Mm-hmm. That's fine. Same thing, different implementation.
Yeah. I think we need to change this. Not sure.
Mm-hmm. Exactly.
Just oh boy, to retrieve the answer from S. I forgot that.
Exactly. Later at the end.
Yeah, as you mentioned.
Mm-hmm.
Okay. Size. Something.
Oh, you got the auto complete, huh?
Yeah.
I like it.
Do you have the auto completed or?
I did on my laptop. I have autocomplete, but I haven't set it up on my new computer yet.
Oh, so it's it's bringing this from my computer. This extension. I didn't know that.
Yeah, it must be. Yeah, it's probably using your extensions. Huh, that's interesting. Yeah, you would
Yeah.
think it would be mine, right?
Yeah, this live sharing extension.
Mm-hmm.
Okay, this is our mirror.
Yep.
Going to be something like I think it was two for our right boundary minus I. I'm going to change this to I. Yeah. If I stress so this is just for update on what I
Yep.
do. It's going to be oh,
Mm-hmm.
we already set this now. Okay. Oh, this is the funny function.
Mm-hmm. This is the expand from center.
Yeah. And modify string for the left. It needs to be equals to the right.
I love this line of code.
Yeah. I didn't know that. I was thinking it was some kind of old algorithm, but I didn't know that the author of this algorithm was a teacher on this university from Chicago.
Yeah, I thought he was like a super old dude or something and maybe passed away
Yeah,
already, but yeah, it turns out he's still alive and teaching at University of Chicago, surprisingly, which is cool. He's in like mathematics and computer science department. Super smart guy, obviously.
yeah, he teaches statistics also. That's why you probably imagine these things.
I know. Well, it's got to come to a point where you learn so many different algorithms that you start being able to like create and connect them even new ones in new and interesting ways. The thing is though, like I would love to be able to write it the way that they write it. Like I read the paper, but it was all like mathematical formulas. I can't read it like that, you know?
Oh, do you mean the formula with this
Yeah.
conditions like a set belongs as it's a subset and
Yeah. If you read
only
if you read the actual paper that he wrote, it's much more difficult to read, you know?
it's like some kind of code.
It's
Yeah,
just symbols, just all symbols.
is a subset belongs
Yeah,
only if
I know. It's next level
it's
stuff right
only
there.
if
I like
yeah
it though.
it was something like this. That's weird
Yeah.
because it's but if you not notice this like some kind of code. Yeah,
Mm. Yeah, I like how they're able to represent programming with mathematics. It's interesting.
yeah. It's- it's-
Exactly. Yep.
So we are going to have a new center.
Hmm.
I and like yeah, so that's okay. Once we have this,
This one too got me. At first, I was like, I thought that you just had to keep track of the longest palindrome as you were iterating through it, but then when I realized that you're actually not keeping track of the longest palindrome, you're keeping track of the current working palindrome because the current working palindrome is what contains the useful information and what allows you to pass information from previous palindromes to future palindromes. And I was like, that was like a big aha moment for me, man. Each one of these super small, simple lines of code are like super beautiful and powerful in their own way, you know?
yeah, yeah, and it's optimized because you are just bringing information with that.
Exactly.
It's
Yeah.
like the two pointer technique, but you are also doing some combination with the key.
Mhm. Mhm. Yeah, it's so cool.
Or okay. And
Now that I think about it, though, I don't even think I used math floor here.
I'm not sure what this means. Let me check. Okay, I think. Towards the end. Oh, I have one. With this one. Yeah. I think.
Let's test it out. Oh,
We have some.
we got a little loop here. Actually, the second answer was wrong, too. We had BAB for the first one. For the second one, we just had B. All right, so let's see. What was returned was... So the function actually finished, but what was returned was short for the second one. Let's see, what was returned? Oh, so what if we have a max palindrome length of 7, but the start is 8? Then it would be 8 to 7. How do we go from 8 to 7?
Oh. It's like a negative one.
Yeah. So we want to start from start, and we want to go into max palindrome length plus something. So if start is 3 and max palindrome length is 7, we want to end. We want to end on 10.
Yeah, you're right. We need to go from start. Yeah.
Yeah, there we.
Going to the end position.
There we go. We still have a that wouldn't have fixed the
Yeah, there is
infinite
some-
loop though. So let's see. Yeah, so we got a correct answer for the second one now. So that these two are good, but we still have an infinite loop here somewhere. So let's see. So while modify string I minus pi minus 1, modify string I plus pi plus 1, increment, that looks good. Return that, modified string, we'll check that function if we don't find anything else. N, fill with zeros, center 0, 0. We are starting at 0, we could start at 1. I think we could even start at 2. I know I started with 1 there just because we know the first one is just a caret symbol. Mirror equals right there. This is definitely a problem. Let me see if there's any. You could think about this one while I check the rest of the code.
Okay. I mean, this is something like the center. Because we are from the center, we are calculating how much we are. Oh, let me 2 times the center minus I.
Could also start here at 1, 2. Yeah, you're right on that though. Because if our right boundary, if our center is 4 and our right boundary is 7, if we did 7 times 7 minus I, let's say I was 6, so we did 7 times 7 minus 7 times 7, which is 14, minus I, which is 6, we would end up with 8. So our mirror would actually end up on the right side of our right
Yeah.
boundary, and it would end up on the right side of our I. So yeah, you got it. Center times 2 minus I. That should be good. And then yeah, let's test it out. BAB, BB. Let's see. Level. D to D. And then alphabet forward, alphabet backwards. Yep, perfect. Good job.
Thanks. I didn't realize that we have to multiply 2 times the center. Yeah, because you are tracking the current algorithm with that information.
Mm-hmm. Exactly. Exactly. Yeah, true. Because if we set the mirror to the other side, then it's always going to be 0. So we're never going to be... Yeah, because if we use right boundary, mirror is always going to be pointing to a 0 value. And if it's always pointing to a 0 value, then we're never taking the information from the left and bringing it to the right.
Yeah.
It's crazy how just such a simple line of code, though, makes such a big difference, though, right?
Yeah. Many times I have this problem sometimes, and but yeah, I say the algorithm is fine, but I getting the wrong answer. But it's just some line of code that I didn't notice, and yeah, I just getting some wrong answers.
Yeah,
But the
yeah.
algorithm was fine. Just the line of code that I wrote.
Yeah. And then it looks like we're not even using the N in the pre-process, so if we're not going to use that, we could just delete those lines of code entirely. Yeah. I mean, you could really clean this up, though, you know what I'm saying? Like, if you take the comments out of it, and then, bro, you could even really just clean this up nicely, you know?
Yeah, but I think pseudocode is also helps a lot, because sometimes I heard about when you are in interview and you don't have enough time to finish your code from the interviewer. He gives you just like 15 minutes, or like, I think I was hearing that sometimes they have like 15 minutes or 30 minutes, and sometimes they give you some medium and easy problem, and you need to solve this too and explain it to the interviewer.
Yeah.
And sometimes you are not going to finish your code, so you can choose explaining by doing several code, and that will help you a lot.
Yeah.
The interviewer will notice that you have the idea, but you have time to implement the solution.
True. It lets you really think through things too.
Yeah.
I agree. Cool, man. I'm gonna hop off. I have another event at 8 o'clock, so I'm gonna hop off, unwind for a couple minutes, and then I'll be back on in a little bit. Did you have any questions though before we take off for a little bit?
No, thanks for explaining the algorithm. I was stuck in the part where we are updating this part, the right boundary, and the part when we are tracking or moving the values from with this mirror.
Mm-hmm.
Yeah, I was a little confused about this.
Yeah.
Why is doing these lines of code? Yeah.
Mm-hmm.
Thanks a lot.
Yeah, for sure. It all makes sense now.
Yeah.
Cool. Awesome. Glad I could help, man. Alrighty. I will. I'll see you sooner than later. I'm sure. We'll chat soon.
Sure.
See you later, man.
Thanks.
Yeah, see ya.
See you later.